Hello and welcome back. In this video we'll be looking at continuity. And I have some example graphs here to start talking about continuity. And the first three, I want to draw your attention to the fact that these lines are going to be unbroken. They're fairly smooth, and in particular, one sort of analogy that math teachers like to use when discussing continuity is that I can draw these without lifting my pen off the paper. So I could just trace these all day, and nothing serious is going to go wrong. These ones down below are a little bit trickier. So for instance, here I have this. I come up here, and then I have to jump up off the paper to get down here and continue tracing. So there's this jump here, and we can see that this line is somehow broken. It is discontinuous. Here I have another shape. So here I'm climbing up, and then I'm just sort of according to the strong, I should be going up forever, and I never cross over. So I have to lift my pen up, jump over, and then continue on down the other side. So again, this is kind of discontinuous, even though both these lines should be getting closer and closer together. Oops. I can't draw very well on this tablet, but you can kind of imagine that they're getting closer and closer together, but they never quite touch way up there. So this we could also think of as discontinuous. And here we've got this nice simple curve. We can trace along it, but there's a point missing right here. So when we're tracing this, we would actually have to jump over that point to continue along the other side. And again, we might consider this discontinuous. So the way that we define mathematically the difference between these guys, the continuous functions, and these guys, the discontinuous functions, is by using limits. So here is the exact definition. A function f is continuous at the point a if the limit as x approaches a is equal to the function value at that point. And there are a couple of hidden things in here. So first of all, I want to look at the right hand side. F of a. So if I can write f of a, that means I should be able to plug a into the function. So hidden in here is the fact that f of a exists. If f of a doesn't exist, I can't plug a in, and my function isn't going to be continuous. So this is one part of this. The other part is that here I have the limit as x approaches a, not from the left or from the right, but from both directions. So over here, what we also need is that the limit as x approaches a, this also has to exist. So hidden in here are a couple of assumptions. Not only does the limit have to be equal to the function value, we have to find the limit first. So it has to exist, which means both the limit from the left and the right have to exist. But also we have to be able to plug a into our function, so we need that f of a also exists. So let's look at some examples, and I think that this is going to be the most helpful thing to do. So here we have a function f of x is equal to 1/2 x plus 1. So we can graph this. We have our y-intercept, which is just going to be up here at plus 1, and our slope is 1/2. So we're going to go up 1 every time we go over 2. So up 1/2, or if we come up 1/2, this is where our point is over here. So we have this line. You just imagine that point crosses through. Okay, so we have this nice straight line. There's nothing really going on with it. It's going to continue going on forever in both directions. We could just continue tracing this line, and we would kind of think of this as a continuous function, right? We never have to lift our pen up off the paper to continue on forever in either direction. So we would expect this to be continuous, and we can check. Let's pick a point right here at x equals 1. We have this point there, and then the question is our function continuous at 1? So is f, the common abbreviation for continuous is CTS, at x equals 1. Well, what do we need to do? We need to check the limit, and we need to check the function value there. So let's check the limit first. So in order to check the limit, we have to check the limit from the left and from the right. So let's check the limit as x approaches 1 from the left. Okay, so here's 1. So as we get closer and closer to x is equal to 1, following our function, we're getting closer and closer to this point right there, which if we look carefully at this, this should be at 1.5. Maybe I'll write this as 3/2. That'll be a little bit easier. Okay, so the limit coming from the left is 3/2. Coming from the other side, as we approach 1 from the right-hand side, we're coming down the function, and we're approaching the same point. It doesn't matter if we're coming from the left or right, we're approaching the same point. So the limit on that side is also 3/2. The last thing to do is to check what happens if I actually just plug 1 into my function. So if I take f of 1, I'm going to get 1/2 times 1 plus 1. Well, 1/2 plus 1, that is 3/2. So they all match. Maybe I don't want those in white. This will be easier to see. All three things match. So the limit is equal to 3/2 because both of the limits from the left and the right match, and the function value is equal to 3/2. So everything works, and we can say that f is continuous at 1. Now, the thing is, 1 really isn't special along here. If I took -1, if I took 0, if I took 3,937, all of those points, our function should be continuous there because the function doesn't change at all. It's just a straight line. It doesn't matter if we're below the x-axis, above the x-axis. It's just a straight line everywhere. So in fact, using the same arguments here, we could say f is continuous everywhere. Now, how do I express everywhere in mathematics? On -infinity to infinity. So it's going to be continuous at every single point from -infinity to infinity. So we can say that this is continuous everywhere. Let's look at another function. Here we've got a piecewise defined function. We've got f of x is going to be equal to x as long as x is less than 1. And f of x is going to be 2 when x is greater than or equal to 1. So let's look at our function here. So for x is less than 1, so here's 1, we are going to be equal to x. So x is just a straight line. It's going to come up, and at 1, we are not defined as x, so I'll leave an empty circle. So this is the line y is equal to x, and we've only drawn it for x is less than 1. Good. So far, so good. Now for x is greater than or equal to 1, we have 2. So we're going to jump up to the height 2. Note that if we're equal to 1, we're at height 2, so I have a closed dot there. And 2 is just a constant function, so we're going to be the same everywhere. So again, let's see, is f continuous at x is equal to 1? Well, we kind of think, oh, I'm jumping up. I can't draw this without lifting my pen up off the paper and then continuing on. So this shouldn't be continuous here, but we can check. let's take the limit as x approaches 1 from the left. So as x approaches 1 from the left, as we come up our line, we can see that we are getting closer and closer to x is equal to 1. Y equal to 1. So the height of our function as we come up from the left is going to approach 1. If we're looking at the right-hand side, as we approach 1 from the right, we have this function, and we're coming over. Our function here is actually going to be at height 2. So right away, we can see that this is not continuous, and in particular, no limit exists. Since the limit as x approaches 1 of f of x does not exist, that means f is not continuous at x equals 1. And that's all we have to say here. We need that the limit exists, and we need that the function value exists, and they have to be equal. Well, if one of them doesn't exist, we can essentially just stop there. The function value does exist, however. So just for posterity, if I plug in if I plug in 1 into f, I can see that I'm going to use this this part of my piecewise function, and f at 1 is going to be equal to 2. So the function value does exist, but the limit doesn't. So our function is not continuous. Let's do another one. We have f of x is equal to x squared for x is less than 0, and it's going to be equal to 1/2 x when x is greater than 0. So again, f of x is going to be equal to x squared for x is less than 0. So this is going to be half a parabola, or we'll start at 0. We're not defined by x squared at 0, so it will be an open circle. And we're going to do something like this. At x is equal to -2, -2 squared is 4, -1, -1 squared should be 1, so we're following the right line here. And then we have 1/2 x. So again, y-intercept is 0, and the slope is going to be 1 over 2. So up 1 over 2, up 1 over 2, and we will continue up. Notice that this line is also not defined at 0. So right away, when I'm looking at this, my function isn't defined at 0 up here. My function isn't defined at 0 down there. My function simply isn't defined at 0. So we could ask, is f continuous at x is equal to 0? And then the answer is no, since f at 1, sorry, not 1, since f of 0 does not exist. And that's all we have to do. So the limit as x approaches 0 might exist, but it can't be equal to this guy because it doesn't exist. Let's actually look at the limit as x approaches 0. If we look at the limit as x approaches 0 from the left, as we follow this our graph down, we can see that we are getting closer and closer to 0. As the limit, if we take the limit as x approaches 0 from the right-hand side, again, we are coming down closer and closer to 0. So in fact, the limit as x approaches 0 does exist and is equal to 0. So even though the limit exists and everything is fine with the limits, we can't plug 0 into our function. So this is discontinuous. There is a gap in the line. So if I were to trace this, I'd have to lift my pen up, skip over the gap, and continue on the other side.